Okay, so let's get started. Yeah, first thing I wanted to say, no news on the contest. It's still yours for the taking, so strongly recommend getting in on that. Some announcements. The first two aren't really announcements, they were announced yesterday, but Homework 2 and Project 2 are now out. Homework 2 due next Wednesday, Project 2 due next Friday. You now have all the material to be able to do both of them. That was the games lectures that we had Monday and Tuesday. And then just a reminder, now that our first project due date is coming up, that you have 5 slip days. 1 slip day is used if you choose to turn in a project 1 day late. And you can use at most 2 on 1 project. If ever this is deep on the course policy page is where this comes from, but if you use up all of your slip days, and then at the end of the semester you need to still turn something in late, you're able to do that. Like edX will let you submit with more than 5 total slip days. We will just choose whichever allocation of the slip days gives you the best grade. So if you really need to wait to turn in project 1 for any reason, don't worry too much about it. Maybe turn in what you have on Friday, but then give yourself the opportunity to turn it in later if you don't finish it by Friday. Even if you're worried about later slip days, it will probably end up being worth it to do that. All right, so today we're still talking about MDPs. Yeah, question? Oh, okay. Sounds like there's some kind of contest login bug. I did not set up the login accounts, so I don't know. I didn't check Piazza about that recently, but I'll talk to the TA who's in charge of that, and we'll get it sorted out quickly. And of course, we'll make an announcement when that is fixed. Thank you for pointing that out. Okay, contest bug will be sorted out as soon as possible. All right, so MDPs II, lecture 2 about MDPs. So where we started yesterday was looking at an example before the mathematical formalism. So let's just recap on that. Forgot to grab pencil. So this is grid world. It's one example of an MDP, but remember that MDPs in general don't have to be maze solving. We saw a couple of different natured examples yesterday, but this is probably the most easy to illustrate all of the important points here. So the robot, similarly to Pac-Man, occupies 1 square on the grid and takes actions to move in some direction. What's different now is that the action can fail, and according to some random outcome, if the robot tries to move north, it could instead end up going west or east if the action fails. This is, if we were to map this to some real world problem, it's a robot whose wheels could slip. So let me erase those. We put some numbers on it, as we'll have to do in all cases that we see. 80% of the time, the action succeeds, and then the other 20% of the time it fails. 10% of that is go west, 10% is go east. Can't go through walls, has to stay in the grid. And the other thing that's new from other problem formulations that we'd seen is that we receive rewards per time step. Now, in grid world, this amounts to a negative living reward at every time step that's not exiting to penalize taking too long to get out of there. And the main source of positive rewards is these exit states. If you make it to the right one, it's a source of positive rewards. And we saw that when the robot gets to here, can take the action right, step to here, and then just the way we've modeled this, which is important for how some of the math is going to work out, is that from this state where the gem is, the robot takes an exit action to a terminal state, and when it takes that transition, it gets the 1 point. Same for the -1. That's when the -1 is accrued on the action that exits the board. This, again, is something that we could have modeled a different way, but this makes the numbers work out most easily. And the goal is to maximize the sum of discounted rewards. We talked yesterday about comparing utilities of different sequences, and the point of discounting was we prefer, if something really good is going to happen, for it to happen sooner rather than later. The easy example I gave was if you're going to get $1 billion today or the day before you die, you prefer to get it today. And someone asked a great question about what about negative rewards? Well, it's still a good model there because let's flip that around. If I say you can either die tomorrow or in 100 years, well, in both cases you're going to die. Which do you prefer? A pretty easy choice. And so this is not only going to make the positive rewards that are distant worth less, it's going to also decrease the magnitude of negative rewards that are distant. In other words, make them more preferable if they're farther away from where we are right now. Any questions about grid world? Okay, good. We saw a bunch of grid world examples. I'll hold off on a demo I want to show that's similar to this. We'll have that a little bit later. So now here's the actual model. And just like when we had search problems, and we had this formalism of these are the different pieces, if you specify it this way, then we have algorithms that will solve it. Here we have states, actions, same as the other kinds of problems we were considering. But now, to account for this model where actions can fail, or more generally, the result of your action is some uncertain outcome, we have a probability distribution over the possible successor states given where you were before, S, and the action you took. So the actual mathematical quantity that it encodes is probability of S prime, our successor state, given S and A. We write it as TSA S prime. And then to account for that living reward and exiting reward, and more generally just the positive or negative reward accrued at each time step, we have a reward function that again is a function of where you started, the action you took, and where you ended up. That triple of where did I start, what did I do, and where did I end up is called one transition. And so reward is a function of the transition. We compared that to the expect-to-max tree by saying that if we start out at S, we're going to choose an action out of our possible actions. That will take us to a chance node, because now there's some uncertain outcome, which is called the Q state. We'll get to that in a second. And then once we're here, there is some probability distribution over the children of this chance node in the expect-to-max tree. The probabilities just come from TSAS prime. And so in that way, we can see one transition, or maybe I should circle over here, one transition in the MDP as performing one ply of expect-to-max search. Or if we're talking about this actually happening in the environment, it's what would happen if we traveled down one branch of this expect-to-max tree. And of course, a start state. Yeah?
Do you need a goal state as well, or only start?
You only need a start. A lot of MDPs that we'll see will have absorbing states or terminal states, where once you get there, nothing's ever going to happen, the game's over. But as we saw yesterday, discounting lets our algorithms converge even when that's not the case. And so since we can handle that, and there are real-world situations that are better modeled that way, we prefer to let all of our algorithms keep operating without that assumption. Quick note about start state, actually, just because you asked. We, in general, also don't necessarily need one start state right now. For the most part, that's what you'll see in 188, but we could just as well have a probability distribution over where we start. And everything still works just as before. And in fact, you can still find a policy in the MDP without knowing your start state. The algorithm we saw yesterday, value iteration, did not depend on what the start state was in any way. This is more just so that after you've performed an algorithm and figured out a policy, to actually act in this world, of course you have to know where your agent is. But this is why you'll see, even though I say this is an important part of an MDP, a lot of problems, the part of the problem we're trying to solve doesn't reference it, so we just won't even talk about start states sometimes. Okay. And then there are these quantities. The first one is policy, which is just a mapping from states to actions. We saw implicit policies defined by our tree search algorithms on Monday and Tuesday, our game tree algorithms, which said, this is an algorithm that I can execute when I know what state I'm in, simulate a bunch of futures, and then choose an action based on the outcome of that computation. With MDPs, the algorithms that we're coming up with here actually give us a policy that is an explicit mapping from each state we could be in to the action we we should take from that state. So that we end up, once we have that policy, with just a reflex agent acting according to a lookup table. The next important one is utility. Remembering back to the lecture where we talked about preferences and coming up with a utility function, in order for us to be able to really choose between all the different sequences of rewards we want, we needed a way to define this. And so we chose sum of discounted rewards. Discounted, remember, just means if we have 1 plus 1 plus 1 onto infinity, because we are in an MDP that doesn't terminate and we can get a reward of 1 at every step, we don't like that. The math doesn't work out well for us because then essentially the value at every state is infinity and we can't reason about anything at all. So we can fix that by decaying the amount that it contributes to our utility exponentially with time. And we also looked at a couple of reasons that, aside from just helping our algorithms work well, this might, or usually is, just preferable, right? If something is good long distance, I was just saying this, it's not as preferable to getting it now. Values, so far we looked at optimal values, V star. It's a function of S, so if we write V star S, then it's the expected utility of, if we're at S right now, acting optimally forever, and, of acting optimally forever. What is the expected sum of discounted rewards that we'll get for that? And then Q values, which again we saw the optimal ones, Q star SA, that's, I'm at S right now. The first action I'm going to take is A, whether A is optimal or not. But then after that, on to infinity, I'm going to act optimally. What is the expected sum of discounted rewards? And so a pretty straightforward relationship between these two quantities emerges, which is that V star S equals max over all of the immediate actions we can take of Q star SA. And we can bring this back to the expect-to-max analogy. V star S, this is before we've chosen an action, and if we're trying to play optimally, we want to choose which action maximizes our utility. That's exactly what we're doing at the max node in the expect-to-max tree. Once we choose that action, we go here. This is called a Q state, and correspondingly, the Q value, that's that expectation over this chance node's children, the utilities of those children. So that was the quick recap of all of the definition stuff we saw yesterday. Yeah? Right. So the question was, how can you have an optimal value, Q star, when it's a chance and it's not up to you? Great question. So the star in Q is actually, remember we're taking action A right now, and then no matter where we end up, we're going to act optimally after that. Star in this Q star right here, this means that whichever one of these children we land in, from there onward, all of the max nodes will be choosing their best node. It's kind of like, suppose we've already done the recursive computation in the expect-to-max tree, and we know what the expected utilities at all of these nodes are. Then Q star here is just the expectation over all of those. It doesn't assume that we know which one we're going to end up in. In fact, that's the computation we're making, is if we know what the value of ending up at each one of those is, take the expectation. Any other questions about MDPs, definitions? Okay. So next thing to recap is what we saw for solving MDPs. We saw one algorithm yesterday called value iteration. So I just went over this. I guess I didn't mention the optimal policy, but of course that's what we want to learn. Of all the policies we could choose, mappings from states to actions, we want the one that's going to maximize our expected future rewards. And yeah, at this point, this is more for reference for you later because we just said all of this. So let's skip forward past that. So you've actually already seen the Bellman equations. We wrote them out yesterday as the way of defining recursively V and Q, but they have a name. We'll see them again in a second, but the idea here, and value iteration is, in a sense, built on this, and we'll see that. These are equations that, remember, define the optimal value as the maximum over all the actions we could take, and then that's an expectation over our immediate reward, and then recursively the optimal value of where we end up. So another way to think about that is the Bellman equations say, first, take the optimal action right now, and then, because this is a recursive definition, wherever you end up, keep acting optimally. Seems kind of tautological here, but as we've seen, this is actually a useful way of thinking about it. So let's actually put those on the board. First one I already said, this is not a Bellman equation, to be clear. This is just a relationship that makes it a little more terse the way we can represent these. So this first one, actually, let's go through deriving that again, because I think that's a valuable exercise. And I recommended, I'll say this again, making sure that you can go through this derivation on your own by next month, Tuesday. Monday's a holiday. That should probably be an announcement. Forgot to say that. In case you forgot, Monday's a holiday. Next lecture is Tuesday. But in the next lecture, we're going to be basically making the MDP problem quite a bit harder by losing some of the information. And we'll be in a situation where we now have to figure out bits of information about the MDP that now are just given to us. As you can imagine, we have these big equations now. They just get bigger when there are more things we have to take into account. So you want to be really comfortable with this by then. So yeah, highly recommended exercise. We're going to do this derivation. Try to do it again on your own and make sure you can reason through the whole thing. You understand why these equations are the way they are. So we want to define Q star of SA. Well, like I said, it's the expectation, and this is notation that is not standard in this class, but just as a starting point, it's the expectation of our first reward plus the discounted utilities that we'll get out of all possible successor states, which, if you remember, that's how we defined V star. So if I write it like that, and this is an expectation over all the different values that S prime could take on, all the different successor states we could end up in, it's R naught, and of course, which reward we get does depend on which S prime we take, so this is a function of that. Again, if you're lost in this notation, don't worry about it. Just follow the words. It's the expectation of next reward and discounted sum of future rewards, which we're supposing we already have for this recursive definition. Well, expectation over S prime. The way we compute an expectation is that as a weighted sum, where the weight on each outcome is the probability of that outcome. So sum over all the S primes of the respective probability, which comes from our transition function, times this value that's in the brackets. So the actual R naught, we can't just write it that way. It has to come from the reward function that's defined as part of the MDP, SAS prime. But then this, that's totally fine. We can leave that as is. Plus gamma V star of S prime. So that's how we get to this point. At a first glance, this may not look totally recursive because we have Q star on the left and V star on the right. But we can combine these two equations that we have on the board, right? This one and this one to get, I won't write it out right now, but V star, actually I will, I'll do it in yellow right here. V star of S equals max over A of Q star SA, which is just this. So now we have this recursive definition of V star. Quick exercise. I'll give you just a few seconds to think about it, talk to your neighbor. How could we make this into a recursive definition for Q star? So take a little bit to think about that. All right, let's bring it back in. Do I have any ideas? Anyone think they figured out how we can modify this equation so that it is a recursive definition of Q star without referencing V star? Yeah.
You could plug in for the V star on the far right, you can plug in max of Q star S prime A.
Yeah, that's the right idea. We're still going to use this equation, and there's just one little piece that's missing. And really the problem is we're talking about different future actions than current actions. A is a name that is already in use for what is our immediate action going to be. So the way we fix that is actually pretty simple. If I were making this into the Q version, it's gamma times the maximum over a different choice of action, A prime, Q star, S prime, A prime. Sorry if you didn't think that was allowed. Maybe I cheated a little bit if you weren't thinking along the lines of adding a new variable. But hopefully you see that all that we just did was unpack this definition by one step. V star right here, use this, transform it into this. And since we're considering a different choice of action, we had to give that a different name. Okay. So I can fill in the slide. It's just these things. And unfortunately, that's very messy. But yeah, all this point says right here is these are the Bellman equations and they're important. Yeah, so just to be clear, and this is a subtlety that is rarely, if ever, important. The Bellman equations are specifically, by definition, let me actually clean that up so you can see this. The Bellman equations are specifically, by definition, the characterizing equations that we have written here for the optimal values and Q values. So when you see the iteration rule for value iteration that has time indexed values, that's technically not the Bellman equation. If ever, it seems like that is a relevant detail. It might be useful to know. But for the most part, what's important to get right now is you can derive this as a recursive definition of what it means to be optimal in an MDP. So last bit to recap is value iteration. So this is the algorithm we saw yesterday. And remember, what we were doing was this dynamic programming approach, bottom up in the search tree. If we are trying to compute the depth limited values for depth 10, then we think about one ply of expectamax. We look one step deeper in the tree. And then if we've already computed all of the values at depth 9, then we can just look those up from the table. We don't have to recurse, and it's a pretty cheap computation. So start with V0 equal to 0, because if you have 0 time steps to accrue any reward, you won't get any reward. And then we do this backup operation, which is the same as doing one ply of expectamax, and then just referencing this VK that we've already computed in a previous iteration. And we saw, since we have a loop right here over all the actions, a loop right here over all the states, one backup. Sometimes when I put my hand on the screen, if you're wondering what that's about, it thinks that I'm like trying to zoom out with the two parts of my palm, and it closes the entire app. It's really bad. One backup, which is running this update equation one time, that takes, well, we just go through both of these loops over actions and states, O of SA. One iteration is to do one backup at every single state. And remember, the point of that is so when we do a next iteration, all of the things that we might want to recurse to compute the higher value have already been computed. So one iteration is just that times the number of times we have to do that, once for each state, S squared A. And we have a theorem that this will converge to the unique optimal values. We're not going to go over that theorem, but some of the theory about this and the other algorithm we're going to see today, if you are a bit more mathematically inclined, about convergence of algorithms, you can read the textbook Sutton and Bardo. It's in the syllabus, a link to it, a couple of chapters that kind of go through more or less all the same material, but with a little more rigorous treatment. That's there as an optional supplement for you. And then we kind of skipped over this yesterday. I'll say a little bit about it right now. But here's the basic idea behind convergence is when we say convergence in an algorithmic sense like this, we're not talking about perfect precision, right? If we wanted perfect precision, then we would have to take the limit to infinity of these iterations, which on actual computational resources, that's just physically impossible. We can't go to infinity. But if we can put a bound on how much the values are ever going to change, then we can have some stopping criterion, like if we know that no matter how many more iterations we run, none of the values are going to, I'll just write it like this, delta V at all states is going to be less than some tiny epsilon, then we stop. And this is the weaker sense of convergence that we actually care about when implementing this algorithm, and this is what we can prove using the tactic on this slide. Quick sketch of the idea is we're trying to talk about the difference between VK and VK plus 1. So we can imagine if we've done VK, that's like an expect-to-max tree that's cut off at depth K. And just for the sake of this argument, I haven't told you why I'm doing this yet, but just say, for now, we add another row at the very bottom, branching out as though we are considering another ply of search, but just all of the rewards are equal to 0. We can do this, and if we do this, then that doesn't change the value at the root at all. It's still the same tree up here in every way. We've just changed the shape of it. And in fact, VK plus 1, after we've run one more iteration of value iteration, it's going to be the same tree above that line. The only difference between these two trees is what's in this bottom row. Now, of course, what's in this bottom row? Well, it could be some R max that's down there. Remember, since we already have all of the rewards along every transition, this is just some constant that's part of the MDP, the max reward along any transition. And then same for R min, which is the most negative thing in there. Everything that lies in here is going to be absolute value of those rewards is going to be less than whichever one of these has bigger absolute value, which means the contribution of this portion of the tree can be bounded by gamma to the k times this bound, which is, as far as we care, let's just call it R max for simplicity, a constant. That's all that matters here. This will get arbitrarily small as we go to infinity. And if you're a really mathematical person and you want to nitpick with me about what about all the future rewards, I'm not going to talk about it here, but it's a pretty straightforward application of the Cauchy-Schwarz inequality. So I'll let you figure that out if you're interested. But we're not going to talk about that in 188. So here's the next bit. Actually, let me ask any questions about convergence. It's not something you're going to have to recall for a test, but it is important to at least have an intuitive belief that this algorithm is going to converge. So any questions about what I just went through? Yeah?
Is there ever a case where the discounts would not be between 0 and 1?
No. By definition, a discount is always between 0 and 1. Sometimes if we have finite horizon MDPs, we can use discount equal to 1, and then we don't have to worry about convergence issues, but never outside that range. Good question. Okay, this is the next type of algorithm we're going to see, but I want to take a break real quick to talk about one scary example of something we saw yesterday happening. So yesterday, we had a slide that had 4 different grid world mazes, and I was just changing the living reward each time. And we saw in the last one, when the living reward was significantly bigger than any reward it could actually get from the final states, from the goal states, it would just rush at any way to get out, no matter the cost. Has anyone seen Rick and Morty? Yeah? Anyone remember Mr. Meeseeks?
Yes.
Yeah. So whoever designed Mr. Meeseeks, it might have been Rick. He never actually says. But he made a mistake in defining the living reward to be a bit too high. So Mr. Meeseeks is essentially an AI who is brought into the world, given a goal, and then it hates being alive, and so it tries as hard as it can to accomplish that goal as quickly as possible so that it can stop existing. Here's what happens when the goal they set for it was too difficult, and so they start coming up with some suboptimal exit strategies.
Look at me! My brothers, nothing will be accomplished by shedding Meeseeks' blood. None of us can die until our job is done. Job can't be done. We'll never get 2 strokes off this game. No, we won't. But we will get all strokes off this game. When we kill him.
And then, yeah, unfortunately I couldn't get one clip that had the whole thing, but here's the rest of that. It gets a little violent, so I'm going to cut it off early.
Jerry! Jerry!
Guys, I'll tough up. I'll follow through. I'll do whatever you tell me to do, okay?
We're well past that, Jerry. Meeseeks and I born into this world, fumbling for meaning, Jerry. We are created to serve a singular purpose for which we will go to any lengths to fulfill. Existence is turning into a Meeseeks, Jerry.
Oh, hang on. There's another video going on in the background. Oh, that's a... Ooh, we don't want to see that. For those of you who know the show, we definitely don't want to see that right now. Okay, I'll go back to here.
Well past that, Jerry. Meeseeks and I born into this world, fumbling for meaning, Jerry. We are created to serve a singular purpose for which we will go to any lengths to fulfill. Existence is pain to a Meeseeks, Jerry, and we will do anything to alleviate that pain.
Okay, so we'll stop it there. But yeah, basically what we saw yesterday. Grid world robot, way too negative living reward, bad stuff can happen. So just remember, define your models well, or you could end up with this. Okay, so back to policy extraction. So, actually, there are a bunch of different concepts that we're going to learn today, which are all policy blank. We haven't gotten to the new thing yet. This is actually part of value iteration, the algorithm, that we kind of glossed over yesterday. This is how, when we run value iteration, we're implicitly computing a policy. The way that works out is like this. So imagine we have all the optimal V star values. How should we act? It's not necessarily obvious, right? When we had the Q values, and if you remember what that looked like, each of these squares was divided into fourths, and we had a value attached to each action we could choose. With that, it was pretty easy. We just pick whichever action had the highest Q value. But with V, because of this uncertainty about what are the results of all our different moves we could take, in grid world, it's still not super difficult to imagine what you want to do, but in general, actions are not as obviously defined as up moves you up. And so you have to actually do a mini expect max, perform one step. And that's the idea of what we're going to do here is we want to say, what's the best action to take right here according to all these optimal values? Well, consider my 4 options. Up, left, down, right. For each one of those, take the expectation of the immediate reward and the value of wherever we're going to end up. This is just basically the Bellman equation. The Bellman equation would be if we perform that computation and then confirm that the number that we get from that is equal to 0.92, or the biggest of all of them. But to compute a policy, we're going to essentially, from the V values, get the Q value. So for the up action, run this one step, and then we're going to know what's the expected value of being here and taking one action, or taking the up action, and then same for all of those, and then just go with whatever action is best. So we get this very similar equation that we've seen several times now. This is called policy extraction since it gets the policy implied by the values. And so one thing you might be wondering is it possible to do a value iteration-like algorithm with Q values instead? Because if we had all the optimal Q values on this plot, then we wouldn't have to, in order to choose an action, do this one more operation that is going to take O of SA time. We wouldn't have to do that. We could just do a constant time calculation. Or at least, I guess, O of A calculation. Because we still have to consider, of all our actions, which has the highest Q value. But that's faster. We would like that better. And there is another algorithm called Q value iteration. And we're not even going to talk about it in lecture because, or with much depth, because it's very similar to value iteration. You'll see it, I believe, on the homework a couple times, maybe in discussion. Just a quick nod to that. The idea is this whole time we've been drawing a part of the expect-to-max tree that looks like this, and one V backup is considering this one ply of expect-to-max search. One Q backup is we kind of reorient the way we're thinking about this so that the plies that we're doing backups on are shaped like this: chance node, max node, chance node. And then other than that, there's nothing different. And the update rule that you use is that equation that we drew a little while ago that is the Bellman equation that is a recursive definition for Q star. There's no V's on there. This is a little bit less intuitive, that this is a way that you would want to think about it. But now seeing this extra step that's left behind by value iteration, you see that there is some motivation for why we might choose to do it this way instead. Oh, I guess I always forget that I have things I'm already wanting to say on the next slide. Okay, so here's actually a drawing of what that looks like. It's a lot easier here because rather than having to calculate that equation a bunch of times, we just look at these four numbers. Which one's biggest? This one. So we take that action. Look at these four numbers. Which one's biggest? This one. So move up, etc. And that's how we get a policy from optimal Q values. So the reason we covered that more explicitly today than we did yesterday, even though it was important yesterday, we were just, like I said, glossing over it, is now we're going to cover an algorithm where that's a bit more of an explicit step in what we're doing. We're going to do that at intermediate steps and then improve on the policy that we find from that. Why would we do this? Why are we not so happy with value iteration? Well, it's slow, S squared, A per iteration. Now, calling that slow right now is you just have to trust me on that that's slow, because I haven't given you any alternative. But this is something that, yeah, problem 2 and problem 3 are kind of the same issue, where if the max at each state is not changing, then the policy is not changing. But this is something that you may have noticed when we were running the demo yesterday. So for the sake of that, being able to see that, I'm going to run our demo from yesterday one more time. So what we're doing here, let me get rid of this. What we're doing right here is running value iteration. After 0 iterations, remember V0 everywhere is 0. After one step, we're going to see the values start to fill in over there. Okay. Now what I want you to notice is, I didn't talk about this yesterday, but there are arrows on the grid, and the arrows correspond to what policy would currently be extracted if we were to stop and assume these are the optimal values. And of course, the more iterations we run, the closer we get to actual convergence. But we'll see that we learn more or less the correct policy way before we see value convergence. So for the sake of this example, imagine our convergence cutoff to be the amount of precision you can see on here. If we don't see a number changing on here, it's at the value it will be forever. Even though probably off at the 0.0001 decimal place, it's still changing a little bit. It's converged for all intents and purposes. So yesterday I said, watch the way the green propagates outward. Now I want you to watch the way the arrows change. we do that, we see some things changing. Keeps going. Okay. No surprises that all of the first few moves are going to make some significant changes. But this is 6 iterations. I just did a couple more. Okay, we just saw the bottom one flip. And so 10 iterations. We're letting this run to 100. And, well, we even saw them stop changing values for what we could see around 30 or so. But we were done in terms of figuring out what policy we wanted to use at 10 iterations. And this is actually pretty typical for a lot of MDPs, is that, especially when you're considering more precision than we are here, your reasonable stopping criterion for convergence of your values is well past what would be the stopping criterion for convergence of policy. And convergence of policy is a much more straightforward notion. It's just our policy is not going to change, no matter how many more iterations we run. We got that around 10, whereas convergence of values was quite a bit later. And there are a couple of slides that illustrate the point for if you want to come back to it and you don't have, and you're just looking at the slides. But yeah, that's what we just saw. So this algorithm is going to exploit that. And the advantage it's going to have over value iteration is that we stop with this once the policy has converged. And we're not worried about accurately estimating the value at every state, because that's not really what we care about. We care about maximizing how much we're going to get, no matter how much that is. So we're not going to have perfect estimates of what the values are, but we are going to have the right policy. So it comes in 2 steps. One is policy evaluation. This is going to be, this actual subroutine that's part of policy iteration is going to look very similar to value iteration. It's just now, instead of assuming that we're trying to act optimally, it's what is the expected utility, if I'm in this state, of acting according to my current policy. We'll talk about how to do that on a slide that will come up pretty soon. And then once we do that, we have some assignment of values to all of the states, like we did after normal value iteration. Only now it's not the optimal values, it's just the values if we follow this policy. And we can do policy improvement, which is now, if we run one step look ahead with the policy that we extract from that, then we can improve it at a local level. We'll see exactly what I mean by that. And the theorem that is important here is that if we keep alternating these two, we'll eventually converge to the global optimum, the optimal policy out of all the policies we could choose. So we'll repeat until it converges. It's called policy iteration. It's still optimal, and the proof that it's optimal is a bit less straightforward. Well, the other one might not have been straightforward either, but this one is even less so than for value iteration. So I have a slide in here where I will give some intuition about it, but I'm not going to give you a proof. You're going to have to kind of believe me. And as we saw, it can converge much faster. Yeah, okay. So let's talk about that first step, policy evaluation. Before, when we were doing value iteration, we were considering do the optimal action, and so we had to do a max at each of the choice nodes right here over all of its children. Now, if we fix the action, fix the policy rather, then we know exactly what action we're going to take at every max node. They're not really max nodes anymore. The choice we are going to make is already made for us. So rather than look at every branch that would come out of this, we fix one. And now the only branching factor is coming out of the chance nodes. This is quite a bit easier to compute. Sorry. Okay, so yeah, this first line is what we saw in the last slide. And the way that we do this, well, we're going to need a different update equation, right? It's not going to be exactly the same as value iteration because we don't have a max anymore. Well, guess what? That's really the difference. We don't have a max anymore. Otherwise, it's going to look the same. So I'm actually going to write this out v pi, as we call it, of v pi of s equals, now before the first thing that we had was a max over actions. No more do we have a max over actions. But we do have an expectation over all successor states because we haven't eliminated the branching factor at the chance node. So sum over these, probability is weighted by t, but this time something slightly different is going to happen in here. A, in our old version of the Bellman equation, was a variable that was defined out here in a max. We were just looping over different values of A. Now, which action are we using? Pi s. Yeah, exactly. We already have a policy that maps, if we're in this state, take this action. So instead of some general action, consider all of the ones we could choose and loop through them successively. There's just one that goes in here. And I'll use a different color for that. I'll use the blue. Pi s. So now instead of SA S prime, S pi S S prime. No surprises there. Maybe it was surprising. In hindsight, maybe it's not. And then, what do we think is going to happen with the reward function? Same thing, right? So, where before this depended on our whole transition, SAS prime, it still does, but we already know which action we're going to take. Pi s. So, now it looks like this. And yeah, the recursion doesn't change at all. So this is our new Bellman equation, and that is also on the slide, if you want to look back at that later. Actually, one thing I want to say about that. If you've taken linear algebra before, if you haven't, you can just kind of ignore me for a minute, but because it's not prereq, so don't worry about it. But you might notice, and it's not super easy to see in this form, but once we've eliminated the max from this, these are all constants. All of the transitions, that's part of the MDP we've defined. These are all constants. All of the rewards, again, just part of the MDP we've defined. Gamma is a constant. All these are constants. The only variables that we're trying to compute right now are, oh, I did something bad. This should be v pi, not v star. Sorry about that. Bad habit, I guess, assuming that we're optimal already. But yeah, so the t's, the r's, and gamma, all constants. The only variables are what are these values that we're trying to compute. So in fact, if you plug in all of these constants, expand out all of these sums, then what you end up getting is one equation for each state in your state space, where on the left side you have v pi of that state, and on the right side you have some linear combination of all of the values of all of the states. If we move everything over to one side, what do we have? It's just a linear system. And so you can actually, for this simplified problem of utilities for a fixed problem, we're no longer trying to find optimal utilities, just for the fixed problem, you can use any kind of linear solver, Gaussian elimination or something more fancy that you might have seen if you've taken some theory classes. So for certain kinds of problems, it's actually going to be a lot faster to exploit that and solve it using linear algebra. And that's, yeah, this is just, we've taken away the only nonlinear part of this, the max, makes it quite a bit easier. Okay. So let's look at a quick example. Here's a board. There's a bridge down the middle, and there's lava on both sides. And here's a policy. Always go right. Seem like a good policy? Yeah? I see some nods. Yeah, pretty good policy. Because of course, our actions could fail. We could just fail 5 times in a row and accidentally move forward and make it to the other side. Perfect. No. It's probably not going to do so well for you. And we want to be able to quantify that, especially because we want to be able to compare it to some other policy, like always go forward. Of course, this seems quite a bit better. So let's see what that looks like with the art gone and numbers in their place. So this is from actually running policy evaluation on those 2 policies. We have, in this board, if you start right here, and you always go right, well, if the reward for going into one of the lava pits is -10, it's pretty likely that you're going to end up down there. And then, even if you don't, you'll slip and go this way, and now you're here, and your policy still says go this way. So this is less negative than what's over here, partially because of the discount factor, but more significantly because there is still some possibility that you could fail all 3 times and make it up to the 100. And it turns out that at this square right here, since you only need to fail in the right direction 1 time, it balances out so that this is just slightly positive. You can expect that always go right at all of these. If you start out right here, you can expect to get a slight positive score. Here's the result of running this algorithm. And when I say this algorithm, I mean the same algorithm we were doing with value iteration, where we just perform those backups over and over and over again. It's the iterative version. We just use that slightly modified equation that we just went through. Or you can do a linear program solver, or linear system solver. So we've done either one of those things. They'll get you the same numbers right here. And not surprisingly, the numbers look a lot better. Notice that the decay is pretty significant. It's not just that we're discounting. I think the discount factor that we used here was 0.9. But also that, remember, if you're all the way back here, to make it to the 100, you have to now succeed. So succeed on an event that happens with probability 0.8 3 times in a row. If you fail even once, you fall off to the side. But that happens with high enough probability that the expected utility of following that policy from here is still positive. Any questions about what this looks like for this example? Okay, great. So, policy evaluation. We turned the recursive Bellman equations into updates. This is something we already did with value iteration, where we had, first we were talking about V star, and that was the Bellman equation. And all we did was time index it and say vk plus 1 is a function of all of this stuff, and vk over here. That's what is meant by turn recursive Bellman equations into updates, like value iteration. Now we're doing the same thing, but with the other formula. Other formula meaning no max here, and pi s everywhere where there was previously an a. And now, if we are doing it the iterative method, the not linear program method, then it's O of s squared per iteration. And why is that less than before? Remember, before we had a loop here over actions and states. We got SA per backup, S backups per iteration, S squared A. Now we don't have a loop over actions, just a loop over states. So O of S per backup and S backups per iteration. And that's how we get that time complexity per iteration. Oh, yeah. Okay. So now let's talk about the algorithm policy iteration. So the first thing we do is evaluation. This is what we're just looking at. For our fixed policy, find the values. Iterate until it converges. Use this over and over and over, and eventually you get, with the same convergence argument we saw before, you get a very, very good estimate of what this value actually is. Once you have that, the next step is improvement. So for fixed values, get a better policy using policy extraction. So when I say policy improvement, it's actually literally the same thing as just policy extraction when we had the result of the V star computation, and we just wanted to grab a policy out of that. So what we've done here, and I haven't really told you why this works yet, but get these estimates. If we follow this utility, this is how well we'll do. And now, based on those estimates, extract a policy. Those aren't the optimal values, so there's no guarantee that this will be the optimal policy. But there actually is a guarantee that we can give that this will be a better policy than it was before. So, quick slide about why does this work. First thing is we have this theorem right here. And here's another one of many theorems that we tell you without proof that is called the policy improvement theorem. And it says if for all s in our set of states, q pi, so q pi means similarly to v pi, this should say s, typo in the slide, sorry. Q pi, so we're in this state. We're going to take this action right here. Notice that's pi prime, a different policy. We'll get to that in a second. But Q pi is just defined as we're in this state. We're going to take some action, and then after that, we're going to follow policy pi. So it's pretty similar to the difference between V star V pi, same difference between Q star Q pi. If it's the case that from our current state, follow this alternate policy pi prime, and we will do at least as well as if we were to just follow pi both at this state and in all future states, then in fact, it would be better for us to just follow pi prime at every state. And the idea behind that is, it almost sounds tautological, but it turns out proving it's not super easy. It's a lot of equations. But you can show that if at every state, following our alternate policy pi prime is better for one step, then we might as well just follow pi prime for all steps, and then all of our potential paths we could take are going to be better. So that's the policy improvement theorem. And from that, we kind of get an intuition for something that looks geometrically like this. It's these dueling subroutines. So we're going back and forth between, imagine that our policy is the best one. If this is the best policy, what are the optimal values? That's just like run value iteration, but fixed to this. And that's this step right here, policy evaluation step. And then we flip it over. We say, okay, imagine these are the optimal values. If that's the case, then what is the optimal policy? And according to the policy improvement theorem, when we do that step, we've actually moved closer to our target, which is over here, the V star and pi star that we actually want to find, the optimal policy. So when we do these alternating constrained optimization problems, think about what it means to converge here. If we've converged, that means our policy did not change. We've hit a fixed point with respect to the equation we're using to update it. And what is that equation? Well, it's actually just the Bellman equation, right? If this is unchanged when we update it, then that means it's actually equal to the max. If the argmax is equal to what it was already set to, then it's a fixed point with respect to a Bellman equation. In other words, it satisfies the equation we use to characterize what it means to be optimal, and so it is the optimal policy. There's some intuition, don't worry too much if you didn't quite follow that, but I hope that helps a little bit in understanding why policy iteration actually works. So we already said most of the points that are going to show up here, but just as a recap, comparing the two algorithms we've seen, value iteration and policy iteration. So in value iteration, every iteration is going to update both the values and implicitly the policy. We can almost imagine, actually it is true, that value iteration is an anytime algorithm like we saw with iterative deepening game tree searches, where if you needed to extract a policy after you've only done 3 iterations of value iteration, you could return a policy right then and there. It wouldn't be the optimal one yet, but if you had more time to compute, you could go to deeper depth, and they'd converge closer and closer to the optimal ones. And at any step along the way, you can return some policy. It'll get better and better, and that's implicitly going on right here. With policy iteration, it has the same property. We always have a policy on hand that we could return if we needed it. It's going to get better and better with time. But this time, we're actually explicitly computing that policy, because for both of those steps, we need to know what policy we're using. We have to have a fixed policy for policy evaluation, that step going up in the geometric diagram, and we need to explicitly compute our best policy with respect to those to do the other steps. So we always have an explicitly computed policy. And either the new policy will be better than the one we had before, or it's a fixed point, so we're done. They're both dynamic programs for solving MDPs. It's a little bit harder to see with policy iteration, but it's also a way of making sure that we don't do the same computations over and over again in going through the expect max tree. One quick note that I want to make about these two algorithms is about this. we are implicitly tracking the policy. You can imagine value iteration as something like do one value backup and then extract a policy, do one value backup and then extract a policy. And that's not in practice the way we do it, but this is a way of kind of unifying our view of these two algorithms. With policy iteration, instead it's fix our policy and do value iteration to convergence, and then based on that, let the policy back up one time to get to where it is. And I left out an important word in what I said before. So back to value iteration is, you can say fix our policy and do one step of value iteration. And then fix those values, do one step of policy iteration. Do that again. And that was because when we're computing this level, this depth limited, say 4, and we've already computed the values at 3, we've implicitly computed the policies, and the values that we have here depend on which policy is going to be best there. So if you don't quite follow that, not important. It's another thing that you can see a lot more detail about in Sutton and Bartow, the book that's linked in the syllabus. But the reason that this is interesting is a lot of algorithms that actually work better than both of these hit a middle ground between that. So value iteration is back and forth, one backup at a time for the value and policy, whereas policy iteration is to convergence and then one backup for the policy to catch up. To convergence, policy catches up. So algorithms that actually work very well are things like just run it for 5 iterations and then policy catches up. And where to choose that constant is kind of an open research problem, really. But if we see this as 2 different variants of the same kind of algorithm, it becomes just a slider that we can adjust to get a bunch of different algorithms that will work well in different scenarios. Okay, so yeah. We've said all these things enough times. So I want to stop now, because this is kind of a preview of what we're going to see next week. But this is a pretty good stopping point to just let you ask questions about MDPs, because I can't stress this enough. It just gets harder, and it builds directly on what we've covered in today's lecture. So more so than before, it's pretty important in order to have kind of a continuous narrative as you come to lecture to make sure that things are clear about this lecture. So I've said a lot of stuff, but we already had no questions when I had the recap on defining MDPs. Let's have this slide up. This is what's important. Do we understand the key ideas behind those 2 algorithms? Are there any questions about value iteration or policy iteration? Anything I can clear up about the Bellman equations too? Any of these things? I'm just going to stand here for a solid minute if you don't think of anything. So, yeah, second row.
We're going to be practicing with this test on this and number 2 or project 2 so that we sort of get to play around with them.
Great question. So question was, will any of this be in homework 2 or project 2? And unfortunately, it won't.
Can you suggest?
Yeah, so, yeah, there. I think, and I can double check this right now, homework 3 is MDPs. And so that would be, if you have the time to do homework 3 early, really valuable, or at least to look over it and maybe do some of the more straightforward, can you apply the algorithm kind of questions. That'd be a really good thing to quiz you for next time. And yeah, I'll double check. I think homework 3 is that. And if that's the case, I'll try to get that out sometime this weekend, which is earlier than we normally would release it just because homework 2 is still going. But yeah, homework 1 ended, okay. But that would be very helpful. Any other questions? Yeah.
I'm still not entirely sure I understand PyStar. Could you talk about how the computer actually interprets it?
Yes. Well, I do have this open right now. I'll do that in just 1 second. I want to pull up, because I have this right here, see what homework 3 is. Yeah, so homework 3 is MDPs, and there are some questions there that will be good practice in prepping for the reinforcement learning we're going to see next lecture. So we'll try to get that out early. And if for any reason that looks like it'll be difficult, maybe we'll release a partial version of it. Okay, yeah, so pi star. So the question is, how does the computer interpret pi star? Is that right? Well, if you're wondering what this would actually look like as a data structure, then there are a few different ways to implement it. Generally what's done, in general, is you just have a function that depends on some internal state that will take in a state, an MDP state, and then return an action. Of course, I mean, that's just kind of what I was saying. But the implementation for the kinds of policies we've seen so far, which is this like really explicit, this state corresponds to this action. We'll see some fuzzier policies later. But that kind of policy can be implemented as a lookup table. So like a hash map, Python dictionary, where key is what is your current state, and plug that in, and it just gives you back what action to take. Does that clear up your question?
Yeah.
Okay, great. Yeah.
So the reason for policy iteration is because of the branching factor of value iteration.
Great
I
question.
don't want to go to the really low levels.
So I did show that on one slide that when we fix the policy, the branching factor in expect max gets quite a bit smaller. But I wouldn't call that the motivation for policy iteration. It's kind of an advantage that makes one of the two steps easier. The real motivation for policy iteration is what we saw right here. And I can run it again, or not. I'll just leave it here. But when you look closely, the policy in terms of the mapping from if we're in this state, take this action, if we're in this state, take this action, that was completely fixed. It has not changed since iteration 10. But the values, according to some more strict criteria than we're using right here, have not yet changed. And in general, value iteration doesn't have a way to know that the policy is not going to change anymore. Value iteration is only concerned with whether or not the values are going to keep changing. And sometimes the convergence criterion for policies is much easier to hit than that for values. And so we end up, sometimes policy iteration finishes in 3 iterations or something like that, 2 iterations, when value iteration would take 100. That's not always the case. And so sometimes it works out that value iteration is faster, but that is certainly something that can happen and does happen pretty often.
You kind of just have to give it a number of value iterations to do between each policy update. Or
Good.
could you like do it by inspection, like if the policy will change because of each value, then update the policy? Or?
Great question. So, yeah, I did say that implicitly we're keeping track of a policy, but just in order for value iteration to be an algorithm that runs pretty quickly, since we're not actually going to use any policies that are intermediate, and we don't need them to compute the next step, we don't need them in any explicit form anyway, we usually don't do that policy extraction step until the very end. And so the condition that you use for stopping for value iteration, for me it's just been kind of arbitrary. Once the point gets across, stop pressing the button. But in real implementations, what you do is you have some epsilon, which is some small amount of deviation, and you say, if I do one more iteration and none of the values change by any more than epsilon, then I can be almost certain that there will be very, very little change in the value. And if you know there's not going to be any significant change in the value, at that point you have pretty serious confidence that the policy has also converged. But it pretty frequently, the policy will have converged way before that point.
Thanks.
Mm-hmm. Yeah.
Say you're actually track of the policy.
Right.
So how do you check the policy has changed?
Yeah, so in value iteration in practice, we don't. We don't, or sorry, let me make sure, value iteration. In value iteration in practice, we do not check on an iteration by iteration basis whether the policy has changed. We have a stopping criterion that's based on how much the values are changing.
So policy iteration, compare policy to iteration.
Exactly. The stopping criterion for policy iteration is after one full iteration our policy didn't change.
And what if it was the case where, like in this example, you do one iteration, policy didn't change, we did another iteration, and the bottom, one of the bottom squares was
Yeah. So when that was happening, the values were still pretty seriously in flux. The numbers, like to the precision we're looking at, which is not very much, they were still changing in that hundredths place. So a reasonable epsilon bound on will stop if the difference after one iteration is less than this, would usually be much less than that. And so if you have a good stopping criterion, which is, say for this, I would do like, if I run an iteration and nothing changes by more than 0.001, then for all intents and purposes, values have converged. Then, because policy usually converges well before that point, the only way the policy could change is if the values were to change in a significant way, and we know now that they're not going to. Then, without even looking at the policy at all, we have this fuzzy guarantee, but still based on some rigorous math, and you can make it more rigorous with a bit more effort, that the policy is not going to change without explicitly computing the policy. Yeah, and this will be the last one. Okay, let me do this. I haven't tried this before, but I think that I can get my iPad screen to broadcast up there, and that would be great. Okay, so here are two algorithms. Okay, we're going to have that thing in the way. Oh well. No. Policy iteration and value iteration. Okay, so should probably have written those in the other order. Talking about value iteration first. This is an algorithm where we just run those backups, those iterations, on until convergence. And my definition of convergence is with some parameter that you can mess with, but usually we just pick some small decimal number, 10 to the negative 5, something like that, epsilon. Then we say if for all s, the absolute difference between vks and vk plus 1 s is less than epsilon, then we know that the values are not going to change by more than epsilon in the future. Because this difference is only going to keep getting smaller as we discount more and more. So this, standing alone, is the stopping criterion. Notice that I don't mention a policy at all right here. But what I'm saying is, this is actually a strong enough condition to tell us, without looking at the policy, that our policy is not going to change if we run more iterations. Now, on the other hand, up here, times it, okay. Up here, we have pi k and pi k plus 1. And our stopping criterion here is for all s, pi k s equals pi k plus 1 s. If this happens, then you know that if you were to run one more iteration, you'd actually be running the exact same iteration you just finished. These are exactly the same. And so you're going to be at this fixed point forever. And so this one, just because this is an algorithm that is explicitly computing policies, we have a stopping criterion that is probably easier to wrap your head around. In a very literal sense, the policy has converged. Down here, we're talking about numbers that implicitly determine the policy, and we have a stopping criterion defined only in terms of those numbers. But in fact, because of this bound, this bound is usually quite a bit smaller than any of the differences that would be necessary to change the policy. So this is a strong enough condition to also guarantee policy convergence. Now, I need to move on, so I'm going to go back to the slides, but if you're still iffy on that, come talk to me after lecture. Okay, so quick preview of next lecture. Now our robot's going to go to the CS-188 casino. He's got 2 slot machines he can play. One of them is very nice. You've probably never seen something like this at a casino. I know I haven't. But look at that blue one. You always win. You go and you pull the lever and you win $1. That's the game. I like that game. But over here, you have something that looks a bit different. A little more typical for a casino because there's actual gambling involved. With some probability, you're going to get $2, and with some probability, you'll get $0. Now, if we were modeling actually a robot playing at a casino, there'd be some cost to playing these games, but for the sake of this illustration, we can kind of ignore that right now. So this is pull a lever, get $1, or pull a lever, get $2, or get 0 with some probability. This is an MDP that models this, and there are 2 states. It's a little bit of a strange model. It's just an artifact of the way that we've defined MDPs. You need, since our reward function is a deterministic function of your transition, there needs to be a way for the transition that happens when you lose on the red game, on the red slot machine, and when you win on the red slot machine to be different. So that's really what the only difference between these states are. As far as what can happen from where you are, no matter which one of these states you're currently in, you're still making the same decision. Am I going to pull the blue lever or the red lever? And the outcomes are still the same. This is just so we can have these separate transitions like this. So actions are blue and red, states are win and lose. Kind of weird to define states that way, but that's why we did that. And what I've said now is the probability that you win on the red one is 0.75. The probability that you lose is 0.25. Now, for the blue one, you win with probability 1, but the reward is 1. When you win on the red one, the probability is $2. And when you lose, it's 0. And we're not discounting for the sake of this illustration. If we do that, then the values, we compute this by value iteration. And we use this time limit. So after 100 steps, what's the best undiscounted sum that you can get? These are the options for the 2 policies, always play red or always play blue. You could have a weirder policy because we defined it this way, that's if I just lost, play this machine, if I just won, play this other one. But these are the only 2 really sensible policies here. So comparing these, yeah, those are the values. And this is what value iteration tells us. What's important to realize about this is we didn't go up there to compute these values. We didn't go play the red slot machine 100 times. This is all a computation that's happening in simulation, in the agent's head. And the word that we're going to use from that, moving forward from here, is offline. This is offline planning. We're not doing it actively by acting in the environment and interacting with it. We're simulating the environment and computing a policy based on that simulation. So now, if we were to play this, maybe we'd get a sequence like this: 2, 2, 0, 2, 2, 2, 2, 0, 0, 0. And, whoops. If you do that, the total sum is 12? A little bit less than the expectation, but that's okay. You know, it's a random sample. Sometimes you get less than the expectation, sometimes you get more. No surprises there. Now we're going to change the situation a little bit. What's different? Aside from the fact that I had to mess up the arrows a bunch because of a bug in Keynote, the other thing that's different here is we don't have numbers on these red transitions anymore. We still know that the blue machine is just going to give you $1 every time. And we still know the structure of this MDP as well. We know that when we play the red slot machine, sometimes we'll win $2 and sometimes we'll lose and get nothing. We just don't know the probabilities yet. So what do we have to do? Well, we can't use the algorithms we've seen so far because we don't have a model of how the MDP would behave. We can't simulate it. So what we actually have to do is switch into online thinking. Actually interact with the environment in order to come up with a plan, a policy. So let's look at this. Let's say we're playing this. We're trying to do some kind of online algorithm to figure out what to do. If we play the red slot machine, and it starts to look like this, 0, 0, 0, 2, 0, 2, 0, 0, 0, 0. Well, that's looking kind of bleak, right? If we were just to go based on this sample, the expectation is we win 1 out of 5 times. And without actually doing the math, that makes it pretty easy to see that this is the better option. Because, yeah, 1/5 is less than 1/2, which would be the equivalent. So there's still a question to ask, though, which is, remember before we got less than the expectation and we said, well, that's okay, that happens. This is a random sample, and so there's going to be some noise, some variance. What if we just got a really bad sample? Maybe there's some value in continuing to try to pull the red lever and get more samples. What if the next 5 samples we get all look like this? Then we're starting to think a little bit differently. We're starting to think, well, unless the probabilities just changed. Leave that out for now. We're assuming stationary models of MDPs. Unless the probabilities changed, that just means that all that happened was we got a really bad sample. And now that we know that, hypothetically, if we chose to do that and we got that outcome, that's going to change a lot what we plan to do. And supposing we chose not to do that, and this was just a bad sample, then now we're just never going to know that in fact we could switch over to the red machine and do a lot better. So this introduces some new kinds of reasoning that we're going to have to think through quite a bit as we get into reinforcement learning next week. So this wasn't planning, it was learning. In the course of interacting with the environment in this way, we gained some knowledge about the way the environment works. We did not know the probabilities at all to begin with, and we took some samples to try to get an estimate of those probabilities. So we had an MDP, but because parts of it were missing, we couldn't just simulate it and solve for the values and get a policy. So we need to interact with the environment in order to figure out what to do. So let's just quickly touch each of these words. Exploration, that's what I was just talking about, where while there's still any question that the probability on that red slot machine could change, we have to weigh our 2 options of if right now the blue one looks better, it might seem tempting to just go to the blue one and pull it forever, get $1 every time. But there's always the possibility that the red one's better and we just have gotten a bad sample. The more samples we take, the more likely it is to converge to the mean. That's that law of large numbers. But we need to come up with a way to actually decide how we're going to deal with that. Exploitation, that's the opposite of exploration. That's, okay, I'm pretty sure the red one's bad. I'm going to stop and just say, for the rest of the time I'm here, I'm going to keep playing the blue slot machine. Regret is now, if we're intentionally choosing moves that we think might be suboptimal, then that means, for the sake of gaining information, we're probably making mistakes with respect to our actual sum of discounted rewards. And regret is a way to quantify the sum of all of those mistakes that we make, whether intentionally or not. And then sampling, we already mentioned. Difficulty, well, the point is, of course, it's about to get a whole lot more difficult. So that's reinforcement learning, and that's what we're going to see next week. That's all for today.